The algebra of electrical circuits. The usefulness of Boolean algebras has become increasingly apparent over the past several decades with the development of the modern computer. The circuit design of computer chips can be expressed in terms of Boolean algebras. In this section, we will develop the Boolean algebra of electrical circuits and switches. However, these results can easily be generalized to the design of integrated computer circuitry.
A switch is a device located at some point in an electrical circuit that controls the flow of current through the circuit. Each switch has two possible states. It can be open and not allow the passage of current through the circuit, or it can be closed and allow the passage of current. These states are mutually exclusive. We require that every switch be in one state or the other. A switch cannot be open and closed at the same time. Also, if one switch is always in the same state as another, we will denote both by the same letter. That is, two switches that are both labeled with the same letter A will always be open at the same time and closed at the same time. Given two switches, we can construct two fundamental types of circuits. Two switches A and B are in series if they make up a circuit of the type that is illustrated in figure 19.3. Current can pass between the terminals A and B in a series circuit only if both of the switches A and B are closed. We will denote this combination of switches by A and B. Two switches A and B are in parallel if they form a circuit of the type that appears in figure 19.4. In the case of a parallel circuit, current can pass between A and B if either one of the switches is closed. We denote a parallel combination of circuits A and B by A or B. We can build more complicated electrical circuits out of series and parallel circuits by replacing any switch in the circuit with one of these two fundamental types of circuits. Circuits constructed in this manner are called series parallel circuits. We will consider two circuits equivalent if they act the same. That is, if we set the switches in equivalent circuits exactly the same, we will obtain the same result. For example, in a series circuit, A and B is exactly the same as B and A. Notice that this is exactly the commutative law for Boolean algebras. In fact, the set of all series parallel circuits forms a Boolean algebra under the operations of V and AND. We can use diagrams to verify the different axioms of a Boolean algebra. The distributive law, A and quantity B or C equals quantity A and B, or quantity A and C, is illustrated in figure 19.5. If A is a switch, then A' is the switch that is always open when A is closed and always closed when A is open. A circuit that is always closed is I in our algebra. A circuit that is always open is O. The laws for A and A' equals O and A or A' equals I are shown in figure 19.6.